Hit record on this computer. Okay. Okay, so Claisen condensations, right? They're kind of slightly modified versions of kind of the aldol additions, aldol condensations. Main difference being you're using an ester, right? And it's kind of like a ester attacking itself instead of like an aldehyde or ketone, right? So in terms of, I guess, the motif you create, you have what's called, what is it? I think it's a alpha beta ketoester, or beta ketoester, right? Which, is like dicarbonyls in general, they're found in a lot of bioactive compounds. So, accessing that kind of, functional group, or, what we call a structural motif, right? It's biologically, I guess, important, synthetically useful. Someone did this, a long, long time ago. I'm guessing their name was Claisen. So let's start with 21.26. Okay. And here we have, so identify the reagents you would use to produce each of the following compounds using a Claisen condensation, right? So here they gave, let's start with this A, right? Okay, so this is interesting actually, because this is one, oh, you'll see it. Okay, I guess we're still having issues on that end. Shouldn't be too bad. And here. Okay, so we have this compound. This is our product, right? And it said basically you want to find the original starting material, right? So it's just, usually on your exam, you'll get the opposite question, right? You get a reaction and think, but I've always liked practicing the reverse because it gives you a it gives you a better understanding of, like, you could, if you're going to go backwards, you can go forwards, right? And it gives you practice both ways because it gives you insight into products before you make them, right? As opposed to just seeing like a set of reagents, right? So here we have our, what is it? Alpha, beta, ketoester. So you could call this, I guess, it doesn't matter which one is alpha or beta, right? I guess this ester group, if anything, could call that the central carbon, and then 1-2 carbons away. Oh, well, here starts the mess. 1-2 carbons away, we have our keto group here, right? So in terms of, let's say if I label these, right? 1. No clue why this thing is. 2. 1, 2, and 3, right? The bond between which carbons is the one that was formed in a Claisen condensation? Two and what, though? Or, 3 and something, or 1 and something. So 2 to 3, right? Okay, so let's break down 2 to 3, right? See what happens, right? If we break these kind of down, right? This is kind of how you actually, let's work backwards, right? So then you'd have, so which which molecule, so we'll have the, I guess, negative charge. I guess technically, right, it could really only be this one because the carbonyl carbon was, Jesus Christ, yeah, sorry guys, this is about to get annoying. Write this in red. So okay, so these are carbons, right? That would mean our, I guess, original thing would look like here. But now if you look at this, right, right, that would mean that this thing attacked this carbonyl, right? But your ester, right, that the whole way this kind of reaction works is your ester group off one of your things is kicked off, right? And that's why, identifying which bond you create is important. It's probably easy to do the reaction going forward. But like I said, identifying the product is important too, because as we can now see, that is not the correct bond that was formed, right? So now if I redraw this, so I said knowing the kind of functional groups you're forming here, right? We can call, we'll call them 1, 2, and 3 again, right? So remember what I said? This is your ester group. This is alpha, beta, right? So the bond you're creating is between alpha and beta. So it's between 2 and 1, right? And that would make sense because if you look at the carbonyl at 1, right, there's no ester there, right? And that would mean it lost its ester to reform the carbonyl, right? So now if we break it up along that bond, abbreviate this as phenyl. Here we have, oops. This is getting annoying. God damn it. I was practicing with the glove earlier. It was going just fine. Now it's deciding to just bug out like crazy. Right. So that was our group here, right? And that would mean originally here, right? It would be your OET, right? And now this would make sense mechanistically. I'm showing this as a concerted mechanism. This is not how the actual mechanism would be, right? But then, right, it would form the bond and then this would reform. I'll actually draw them in different color arrows, right? The second step, you have this kicks off, right? And that would form the bond, right? So basically the kind of carbonyl that doesn't have the OET, right? That's the one, it's obviously forming the ketone part of this whole compound, but that's the one that lost its ester group, right? And this makes sense too, because, this is an example of what, is it like is it a cross cladosin or is this a regular cladosin? Cross, right? We have two different carbonyls. We have two different esters, right? That's kind of how these things form. But also, let's examine these two products, right? If we just looked at them just as is, right? Can you even form any other products, right? Could have this, the one with the phenyl ring on it, right? The one on the left here, right? Could that he have even formed like an enolate? Why not? No hydrogens, right? So this is like something which is kind of important in terms of enolate chemistry, like for product, like when you're doing, I guess, when you're taking synthesis into account, when you're like taking that question with reactions into account, right? is identifying if you have the right kind of reagent to do your reaction, because like if there's no hydrogens here, right? If we look at this full structure, right, this is a phenyl ring directly attached, right? It has no alpha hydrogens. It could never have formed an enolate, right? Here, though, we came from one side that had the alkyl group and still it's ester intact, right? So of course that could form an enolate pretty well because it does have the alpha hydrogen, right? So this is something to take into consideration for like, what is it, usually question 3 or 4, right? If you're given one of these chapter 21 reactions, right, make sure you actually have a hydrogen there to do the reaction with. Otherwise, it would be no reaction, right? And this applies to not just Clasons, it's for aldol and aldol additions, aldol, condensations as well, right? Okay. Yeah, I mean, the Clason's pretty straightforward. Like, I mean, if I just made up a problem, let's say like, um, oh, Jesus Christ. Yep, I really thought this glove would really help. I mean, honestly, let's see if I take it off. If it helps, maybe that might be bugging out the pen. Actually, I think it was. Oh, just the old laptop and the. Give me a second. Glove back on. Okay. And let's have this bottom one here too. Okay. So those are 2 reactions, right? Um, so take a minute and give me the products. These are not in your textbook. I literally just drew them up. But one thing I just want to ask, just to keep everyone on their toes, is does it matter what base we use here to do a Clason reaction, Clason condensation? Right. You could use OH, right? That would be fine. What about any other alkoxide base though? Well, actually, I don't know if you can use hydroxide. Wait, did he mention this in class? Yeah, okay, he did. All right, so yeah, Hamad has it there. Yeah, that's really what I was trying to get at. It's that's the key here, right? So if I was using OMEs, right, or like if you're starting material, or like you're doing a synthesis or something like that, right? make sure the kind of it's best to wow, what the heck? It's best to uh, match your base with the OR group of your ester, right? The whole reason being is if you use hydroxide, I'm pretty sure you'll get a carboxylic acid, which is bad because it's a good nucleophile, so it'll make a carboxylic acid. Another thing that would happen if you use something like another alkoxide, like methoxide, or I guess maybe even propyl oxide or some shit like that. You'll get transesterification, right? So basically your OET would stop out with the OME, and that might not be something you could do. So with the so it's fine with the aldehydes, right? Your choice of base doesn't matter. Well, until we get to alkylation stuff, then you might have to pick like LDA versus NaH, but that's a matter of kinetics versus thermodynamics. So for the aldol stuff, your choice of base doesn't matter which one you use. But for the Claisen stuff, because of the ester group, right, and the ability for the your base to kind of swap out for it, right? You could get a carboxylic acid or a different ester side product, which is undesirable, right? So generally, it's the same OR group here used as the base, right? Okay. So for the first one, you guys get a product. A over here. Obviously, you guys can't edit the OneNote, but anyone get a product? Okay. Well, yeah, no, it's kind of hard to without you guys being able to write or like share your screens or something like that, or your thing. It's going to be obviously difficult for me to see what you guys think, but the whole point of the first question, right, is there's no reaction. Like, why? No hydrogens, right? So you got something like this, right? The whole point is understanding that this kind of chemistry occurs mainly because of the acidity of your alpha hydrogen. There are 3 methyl groups. It's a terbutyl group. There's no hydrogens. They're all at beta positions. Therefore, you're not going to have any sort of reaction here. The second one, you do have 2 alpha hydrogens, right? So I can start off the process by basically converting this into your enolate, and then it's going to attack itself. So to say this is OET, right? Right. Draw an arrow, right? It's going to kick up this way. Obviously, in the second step, part would just kick off. Now we have our basically new alkyl structure, right? So draw it a little. My bad. These are going to be very sloppy because I'm trying to make sure I could actually draw these without bugging out the computer. So this is now the next carbonyl. Right. There we go. That should be it. Right. That should be your product, right? I'm missing something though. I'm missing. There you go. All right. So we have our beta keto ester, right? As a result of that. Pretty straightforward, right? Clayson, very similar to your things here. Okay, let's move on to alkylations. But give me 1 minute. I need to see if I could fix this goddamn stylus. Yeah, give me a minute. I'll go over the orange arrows too. Okay, sorry about that. Zoom share. Hopefully this should be a little bit better here. Okay, so who has the orange arrows? Yeah, the orange arrows is basically, so after the pink step, right, we basically form, what is it? If I erase a little bit of this here, right? This will be a little easier to see. Basically, you have right? So that's after the pink step, right? And then what happens here, right, is this is your tetrahedral intermediate, right? And then this just reforms your carbonyl and kicks that off, right? And that forms your final product, which is going to be the carbonyl here. Oops, let's change the color back to orange. Okay, all right. So that's it. I just drew it in one thing just to save some time since the mechanism we've already seen before. Okay. Let's do alkylations. When is the guy's third exam for Bisco people? I know people in Boson's class have an exam this coming week. But what about for Bisco? December 9th. My apps will be in by then. So listen, the thing is, this whole stylish thing is just it's annoying the shit out of me, and it's like spending so much time, trying to make sure I could write stuff properly. What I'm probably gonna do today is I'm just gonna finish up chapter 21, right? So once we finish up that, I'm gonna just end the session there. And then, well, next week we don't have recitations, Thanksgiving weekend, right? So then I'll have to schedule something in between the 1st and the 9th, right? So 4th, obviously, we'll have a recitation, right, as normally scheduled. So yeah, one of those days, probably the 5th. We can do 4th and 5th back to back. So 4th, we could do the amines chapter. 5th, we could do carbohydrates. You guys should be done by that. Maybe an exam review one of those days, maybe 7, the night of the 7th. I mean, you guys already have one on the 7th. Professor Bisco usually does that. So yeah, that's what we'll do. So we're just gonna finish up the chapter 21 today because this is wasting this way too much time trying to make sure I can write properly. And I know I'll have my stuff by the next recitation time. So yeah, that's what we'll do. And I let my Orgo 1 class know too, but yeah, that week of December 5th, and then the week of December 5th, I'm gonna be available in person. I'm gonna try to make a slot during the afternoon times on campus, right? So there's gonna be probably, I mean, I don't know how many Orgo 1 kids would come, but it's just open to anyone for Orgo questions. So if people want before their final, before the 3rd exam, any questions, I will be in Marshak at some time. So yeah, okay, let's just get back to the chemistry. Okay, so alkylations, right, which is kind of a matter of kinetics versus thermodynamics, right? Let's do this. 21.29 is a good question. We have a Okay, so we have this reaction, right? So once again, what's the function of LDA? What's it gonna do? Nucleophile, electrophile, base, acid, bulky base, right? That's important, right? So it's a bulky base, right? And what about that temperature? Obviously, it's very low temperature, right? So in terms of kind of reaction pathways, which you guys did earlier this semester too, that's why I said temperature is kind of important in terms of favoring one thing over the other, right? Is this gonna basically, I guess my point being is it gonna promote the kinetic enolate or the thermodynamic enolate? That's not a high temperature. It's negative 78 degrees Celsius. It's pretty damn low. um, but yes, it's going to be a kinetic, right? Because first we have a bulky base, right? Um, so, the first thing with the bulky base is that it's going to be selective. It's going to grab it from the more hindered or less hindered position. Or the places with more H's or the place with less H's, however you want to look at it. Right? The less hindered, right? If it's remember LDA looks like an diisopropyl amine. Pretty sure this should be the structure. Um, so yeah, the place with more H is obviously available. So that's LDA, right? Supersterically hindered base, right? We have a very low temperature, right? So the pathway we're faming is for the kinetic enolate. We're basically uh, saying that the base is going to be selective towards the less hindered position, right? And our final product won't be as stable as the other one to a degree. Well, it's not really about the stability. It's more about the stability of the, I guess, intermediate, right? So anyways, first step, right, is just a deprotonation. So I'm just gonna write this as B, right? And we can just grab an H. Um, you know what? Let's actually show the full enolate here. And you have that. That's going to be O minus, right? Now, second step, what's the role of the methyl iodide here? Well, what's its role? Yeah, it is going to be a SN2 type reaction, right? So that's right. But nucleophile or electrophile? Electrophile. Good. Right. So if I draw this out a little bit. Like you said, it's one of those days. Whoops, should attack the carbon there. Fix that arrow a little. And that's going to kick off, right? And now you have your final product, which is your alkylated thing. And it's going to be alkylated on the less hindered position, right? So this is now methyl here, and this is that. Right. And the reality is, right, you're not going to get 100% of this anyways, right? Because you have a base, right, there's also still a chance of an aldol reaction occurring, right, an aldol additioning in this case, right? But you'll get a good yield of it. And that's why we kind of lower the temperature to prevent, first of all, the thermodynamic enolate from forming, and second, um, well, in this case, right, yeah, you would probably use your electrophile here as your limiting reagent to prevent further alkylations, because that's definitely an issue here, is that if you have too much base, basically it can deprotonate this and then do another alkylation, right? But that's why you kind of control the amount of everything you have present there to avoid that kind of thing. That's kind of good to think about, right, in terms of like how you would actually run this in real life and things that could occur, right? Uh, yeah, so that's the kinetic version, right? And then I don't know if he mentioned in class, but did he kind of mention how you can achieve this kind of temperature in a lab setting? I don't think you'll ever do it in an orgo lab, but the avatar. uh, no, so actually a very cheap way to get this thing. It's just if you put dry ice, you mash up a bunch of dry ice. It's if you want to look this up, these are called cooling baths, right? There's a lot of them are based off dry ice, and this one is specifically with acetone. I actually did this earlier this week for one of my reactions because it had to occur specifically at negative 75 or above, or below, I should say, right? So you literally just take a bunch of dry ice. It's better to have it as crushed as possible. The only downside is you have to keep replenishing it, and then you just fill it up with acetone, and then that bath, right? Because I guess freezing point of carbon dioxide is around negative 78, and acetone can handle that pretty well. So that cooling bath goes all the way to negative 78, and it's a very cheap way of getting a low temperature, right? Obviously, if you want something lower, you're probably going to have to start venturing into cryo coolers or liquid nitrogen. But those are annoying to work. Oh, cryo coolers are expensive, but liquid nitrogen is annoying to work with. Okay, so let's do one more example of alkylation. You could just buy it. I mean, dry ice is actually available in retail too. We just get a delivery every week. Actually, it's someone not too far from the school who delivers it. But I'm sure you could find dry ice easily. Plus, as a consumer too, you don't need to work in a lab or anything to use it. A lot of people use it for like showboating effects because it has the kind of fog, right? So it makes a presentation look nice or something like that. Um, I'm sure you could find it somewhere. If you just look up dry ice in Google Maps, maybe there's a nearby retailer. You don't need like a chemical license for it. Okay, let's do one more. Let's do this one, B. Give you guys a minute to do this. Really just want to make sure I can get to the well, I mean, we're going to cover this entire chapter, so that's not too big of an issue. And we'll do some synthesis problems with this too. I'll end on that. So here we have this. Just going to put the circle in here instead of the pi bonds. Okay. Okay. So NaH, not really a temperature mentioned, which usually kind of means it's room temperature, right? Maybe slightly elevated, probably not slightly elevated because that might destroy your carbonyl. But which is it gonna grab a hydrogen off the left side or the right side? But think about this question though. Left, right, both? Okay, so everyone's saying right. Right, so NaH, right? So the truth is it's actually both, right? But this is where thermodynamics comes into play, right? Is that when you when you have enough time or energy, right? What it's gonna want to do is it's gonna want to create the more stable intermediate. That's why I drew out this over here, because if you if you look at this double bond here, right, it's di substituted, right? So if we kind of consider this an alkene, right, it's, somewhat stable, right? But if we formed it on the other side, it would have been tri-substituted, which is slightly more stable. So the difference here is NaH, right? It's gonna grab protons from both sides since they're both accessible. The only thing here is H minus, right? Which is a very small non-nucleophilic base, right? Um, and the thing is, though, it's going to, over time, it's going to grab the protons more off the left side, right? Because when we grab that proton, right, deprotonate it and the enolate, right? Now, if I'll just redraw it, right? Our enolate will look like this. Right? So it's more substituted, right? And we have enough temperature, right, to kind of go through that pathway, because the main issue with that pathway is it requires a little bit more energy, right? Both sides are correct, but like in terms of if you're asked a question about this, you always pick the more substituted side when you have a less hindered base like NaH, right? So whenever you see NaH followed by some sort of electrophile like alkyl electrophile or something like that, right? You're looking to basically alkylate it at the uh, uh, more hindered position or more substituted position, right? And the reason being is that intermediate that goes through here is more stabilized because this double bond, right, is tetrasubstituted, as opposed to on the other side it would be tri, right? And then the next step that happens here is, right, that just attacks your um, exactly, right? So the pathway it kind of takes, pretty sure there's a table here, and not table, yeah, on page 980 in your textbook, they have a nice little diagram that kind of demonstrates this, right? And this is why the temperature is important, right? Because at lower temperature, you prevent the reaction from going through the other pathway, right? This is the thermodynamic pathway, right? So when you lower the temperature, just like we did in the conjugated pi systems, right? It's going to form the product that can just form faster, right? It's going to favor that, right? But when you have more temperature, you have more kinetic energy available, right? It's going to basically allow it to go through the higher, I guess, energy pathway, which leads to a lower energy product technically, right? Or lower energy intermediate, however you want to look at it, right? But that's a kind of key thing with these alkylations, right? Whenever you see a big bulky base, right? LDA, yes, terbiute oxide will be fine too, and a low temperature. It's going for the less hindered position, aka the kinetic enolate. Maybe I'll write that here. Oh, okay, this is kind of working. This one is going to be thermodynamic here. Okay, right? And now what happens here, right, is this is just going to attack our electrophile here, right? I'm just going to draw an arrow. Let me just erase these circles, right? Attack at this. Okay, there we go. Our final product. Should be a 5-membered ring. Just gonna write pH up here. Sorry about that. It's just, I don't know, this thing is just bugging out more and more as we're going down, and I realize my screen isn't sharing either. God damn. Okay, so yeah, that's the product you're gonna form. Right, just going to attack at the thing. So key things here, right? Bulky base, low temperature, kinetic, less hindered position, non-bulky base. It's gonna be at the more hindered position. You get your thermodynamic product, right? And high temperatures, right? Or moderate to high, however you want to look at it. Okay, all right. So let's do some examples of malonic and acetoacetic ester synthesis. And then we can do some, basically just finish off with the conjugate addition reactions. For B, yeah, the major product, right? Your alkyl group in this case will be at the more substituted position, right? So, and if you think about it in terms of like sterically, right? LDA is more likely to go to the less hindered position. NaH is super small, right? So it can grab the proton from the more hindered position because it's going to form a more stable intermediate, as we saw that on the left here that I'm going to zoom in on, right? This is tetrasubstituted, right? And NaH would rather form that because, you know, it's more stable. And I just want to point out though that it's able to grab protons off both sides, right? In the end, it's still a base, right? It's just it's more likely to the other one because of, you know, or I guess our energy considerations here, right? And our conditions in general favor that, right? This is kind of one thing I just want to point out is one of the things I guess a lot of people always have a bit difficulty with organic chem is you can't change the function of something, right? If something's a base, it's going to be a base, right? And if there's things that are acidic, it's going to, you know, deprotonate them or react with them, right? And this is kind of this one thing I hope people think about is like, you know, there'll always be side products, right? I mean, sometimes you can make good conditions to avoid that, but like things can always act another way, right? So it's just like, you know, that's why I always say don't just memorize it, you know, kind of try to think of what it's acting as, because then you could always figure out what a reaction is. That's why, you know, the whole thing I've been repeating throughout the semester, identify the nature of your reagents. It's the best way to always just look at organic chem, right? Because, you know, it might be a nucleophile in one reaction, it might be a base in another reaction, something like that, right? or something might be an acid in one reaction, it might be an electrophile in another reaction, right? Okay, let's do example of malonic ester. Actually, let's take a 5-minute break here. It's 1 o'clock, so we'll take a 5-minute break and then we'll just do the rest of this for how much, I don't know how much time it's gonna take, but we're just gonna finish up 21 today. So I will be back. Okay. So this is an example of malonic ester synthesis, right? I'll give you guys a minute or two to attempt it, right? So this is what is it? Diethylmalonate, I guess it would be called. Yeah. Yeah. So one thing to note, right? It's once again, right? This could be anything that looks like this, right? So this, right? If you had two carboxylic acids here, right? These are this is what's called malonic acid, right? This means there's one carbon in between the two. It's an example of a dicarboxylic acid, right? So if you had any OR groups here, right, the same reaction can occur, right? So I just want to point it out. It's not limited to just ET groups there. You could see OMEs here, right? The main difference then there would be in terms of the base, right? I would just use NaOMe, right? So I just want to point out, right, that once again, if you see this on your exam as like OME and OME, it's the same type of reaction, right? The only thing that's kind of different is the ester group is slightly modified for whatever reason that might be, right? But the chemistry still occurs the same way, right? So take a minute or two to kind of do that and, do the first step. You don't have to show the mechanism, right? Good to show the intermediates. That's what I'll do as well, right? Let's start off with that for the first step, right? So after step one, maybe I'll go down here. After step one, right, we're going to have first intermediate. Oops. Right, that just deprotonated it, right? Next step, we have an alkyl halide, right? So we have a nucleophile here, we have an electrophile, right? They react with each other. This is typical SN2 type reaction, right? So we had how many carbons there? It was an ethyl group. So we are attaching 2 carbons. Yeah, I'm like on the verge of punching this, like to start bashing this laptop. I gotta remember that is the only thing I could use for the next 2 weeks. Okay, so just be careful though when we create these bonds, right? You're adding 2 carbons here, right? So, oh, I actually messed up too. Good thing I saw that, right? So this is to the first carbon and 2 carbons, right? Same thing here, right? Don't add extra carbons here. Okay, now next step is deprotonation again. So now we have, that's why another molecule of base comes in, right? Forgot my OET here. Right. And now we have our second electrophile, which was the cyclohexyl thing, right? So now that's gonna be attacked by this nucleophile. And now we get this. So you could also just like, you might only see this with just one alkylation, right? So this specific example I kind of made up was with the dialkylation, right? So just wanted to point out here, right, that technically, right, it's still considered a malonic ester synthesis if you just stop at the first, at step 2, right? We're just dialkylating it here in case you get something like this on your exam with up to four steps for one of those things. Right? All you're doing is the same thing twice, essentially, right? With the 5th step being slightly different. Okay, so this OET. That's one group. And this is our next group. We have 1 carbon it's attached to, and then the cyclohexyl ring. Go. Okay, so that's after step 4, right? Now off the 5th step, which is H3O plus, right? What does that do when you have 2 ester groups or ester groups and you introduce it to acid catalyzed conditions, right? It's going to turn both into carboxylic acids, right? So now we have our malonic acid technically dialkylated, right? Whoops, these should be OHs. Thank you. Okay, right? And then we have acid catalyzed conditions under high temperatures. So when you have this, it's probably cranked up past 100 Cs, right? And what does the heat do, right? Basically the high temperature part. What's that? What's it gonna do here? Mm, kinda. I mean, it is like an intramolecular thing that happens, right? But the process is called decarboxylation, right? You know, maybe for those who have dabbled in like with weed and stuff, there's something called like decarbing your weed, right? That's literally the process is removing carboxylic acid groups, right? So yeah, or really removing carbon CO2, which gets left behind as whatever the resulting thing is. But that's the whole decarboxylation process. Um, well, what does it do in this example, or in terms of the the drug example I gave? It activates it. That gives you your activated THC, and that's what actually gets you high. um, that's what burning weed does, right? So naturally, you find a substance called THCA, right? In the what's it called? Actual like cannabis, like actual like the natural leaves or buds or whatever you want to call it, right? Um, and that right is decarboxylated, right? So yeah, let me finish this problem. I might as well just show you guys a real life example of what happens, right? So you know what's happening when you're putting stuff into your lungs. So anyways, what happens here really is if I read through this, this, I guess I could flip this one over here. It doesn't matter which one you choose. Just need to Okay, so you guys probably saw this in class, right? It forms a kind of six-member transition state here. I think you probably mentioned this, right? Um, so it forms your six-member transition state. I wish I could draw a little better, right? And then basically what happens here is, so this is going to grab the proton, right? This is going to push down this way, right? These you could just say form the double bond here, and what am I missing here? Oh, whoops. It should be slightly different. Give me a second. That's still our H here. It should be like this. There we go. And there we go. 3 arrows. I was like, why am I getting 4 arrows? That should be it. All right. So you could just say this kind of double bond attacks, protonates here, right? It really forms two OHs. So it's weird to see here, but essentially what's happening on this side of the molecule is CO2 is leaving, right? So you're basically getting rid of CO2, right? That's the decarboxylation part, right? Then you actually form like, I guess, geminal dienol, whatever you want to call it, but that just tautomerizes, right? And basically at the end of all of this, essentially, it's this a whole step, the process just kind of creates the final product that looks like this, right? So essentially, it just cleaves off your CO2H group, right? And then you have access to this, which is a 1,2. So I guess it would be a 2,2 disubstituted carboxylic acid. So that structural motif might, I'm sure, is probably prevalent in a lot of natural compounds, right? So that's kind of the main point of this, is to access this kind of functionalization, right? Double bond. Well, that's after I skipped the kind of tautomer, right? So technically you have a double bond and it's gonna, what comes before here looks like this. This is what I was saying, the diol, right? The diol that looks like this, right? And then a tautomization happens, right? And then you have, right, tautomization is just the internal proton transfer, right? And you could just write it like that. I think let me see where the book has it. This example isn't in your book. I just made up the example based off one of your book questions, the one they already solved in the book. Like I said, the chemistry is all the same. Page, where's the decarboxylation part? Main part I just want to link to y'all. The heck? There you go. 982, right? If you wanna, they drew it a little better because obviously I'm limited by this crappy stylus here, and this old ass computer. But they have a nice little thing where they basically showed the decarboxylation part with the CO2 leaving. Then they showed the original tautomer, and then they showed the final carboxylic acid tautomer, right? The only difference there is they had a mono-substituted carboxylic acid. Here we have a di-substituted, right? Okay, so acetoacetic synthesis is it's literally the same thing. The only difference here, right, would be, instead of using this as a starting material, right, I would use so instead of a I guess a diester or whatever you want to call it, right? This would be a beta ketoester technically, right? So you have your acetate group there, really. And then the chemistry is all the same because, right, this whole chapter is chemistry at the alpha carbon, right? So all the chemistry is still occurring here, right? So your final product, right, is going to, well, first let's draw. So basically up until step 5, we're going to get something that looks like this if we put it through the same reaction conditions, right? So instead of 2 carboxylic acid groups, we're going to have 1 carboxylic acid group because the other group is a ketone, acetyl group, whatever you want to call it. And then we have our 2 R groups here. Right. This is our carboxylic acid, right? And then obviously after that ends, you could just, the heat decarboxylates it, and you get your final product, which is just, like I said, the main difference between acetoacetic and malonic is the functional group at the end. Here you get a carboxylic acid, there you get a ketone, right? That's the main difference. Even though they have like full pages written onto it, the chemistry is all the same, right? It's all at that alpha carbon. It's just it's really just certain functional groups that are different. That's the main difference in all this chapter. Okay, so that's all for the alkylation type reactions, right? So we did the simple alkylations, which was just using, any ketone or aldehyde, right? You could use LDA, NaH. Then you had the more specialized versions, which was malonic, and this acetoacetic, right? The main difference is malonic forms a carboxylic acid, acetoacetic forms a ketone, right? You could mono-substitute them or you could di-substitute them, right? That just depends on how much of your electrophile you use, right? Okay, let's move on to the final part of this chapter, which is the conjugate additions, aka the Michael reactions, right? So a lot of the products that we formed earlier, right, like the unsaturated aldehydes and I guess your diols or whatever, right? We can basically do what's called Michael addition. So I don't know how much in detail he went because obviously this is still an undergraduate level class. But like this has to basically do with, I'm pretty sure it has to do with hardness and softness. This is something called hard, soft, acid-base theory. I don't know if you mention it. Basically, you could describe nucleophiles, electrophiles as like hard or soft, right? And the main reason this chemistry occurs is because of the types of electrophiles and nucleophiles you have here. Like I guess here would be soft interactions. I don't want to say, I haven't looked at it in a while. But it's basically carbon-carbon bond forming reactions, right? So in your chapter, there's a nice little table, right? I'm just gonna copy and paste it here because I want to describe what the kind of main thing is with your Michael donors and acceptors. It's pretty easy to think about, right? Once again, you don't have to memorize this table, just understand what's being shown here. So let's do that. Okay. So these are your list of common Michael donors and acceptors, right? If you looked at it, right, the Michael donor is something that's nucleophilic. So it's usually, and it's somewhat stabilized to a degree, right? You have dicarbonyls, all of them. The only exception there is the Gilman reagents, right? But the whole point is all donors, right, are electron rich, all acceptors are electron poor. But the main thing here with these reactions, right, this is what I said in terms of soft reaction, hard reaction, stuff like that, is the position it attacks, right, is not the carbonyl, right? So maybe I'll put a red mark here, right? Because technically, right, you have two electrophilic positions on all this stuff that are considered acceptors, right? But these specific nucleophiles, right, they're selective, right? And they only attack at the pi bond here, the carbon pi bond or the end of your alkene where your unsaturation is here, right? So I'll erase the rest, but that's the main thing is why this is this kind of a useful reaction is it gives you kind of selective control. Like what if you wanted to add something at that position, right? And without disturbing your carbonyl, now you have a way of doing it, right? So you have all these various nucleophiles and they'll add at kind of the beta position, if you want to think about it that way, right? Away from some sort of, what are these, all these groups attached? What are these? Electron withdrawing, electron donating? Are they donating? NO2, nitrile, carbonyls, right? They all have some sort of either partial positive, fully positive, or some partial positive charge, or some conjugation withdrawing electron density, right? Because the main thing is the reason what makes this so electrophilic, right, is this thing can go like here, right? Yeah, CN withdraws is a triple bond, right? Nitrogen can still take right, like this, right? And NO2 has a plus charge on it, right? Anything that's has pi bonds is a withdrawing group to a degree, right? So like the nitrile acts similar to how a carbonyl does. The only difference is the triple bond, right? But it's still a pi bond, right? Which can be easily broken, right? Um, so yeah, Michael donors are nucleophilic, usually some sort of dicarbonyl thing that could be deprotonated at your alpha position. The only kind of additional stuff here, right? They all still have withdrawing groups too here, right? Look at all of these, right? The main difference though is in between those groups is some sort of nucleophilic position. Here you have an electrophilic position nearby because of that unsaturation. And that's kind of the key here is there's that unsaturation, the alpha beta unsaturation that makes that position very electrophilic, right? So Michael donors electron rich, Michael acceptors electron poor, right? Same thing, right? They're just selective that the donors will attack at that position, the non-carbonyl position, the beta position, right? So they're useful reactions to, for synthesis or whatever. And that's kind of really the game with synthesis for the last 20 years or so is that, I mean, everyone, for the most part, we have discovered majority of ways to create certain functional groups and functionalize certain things, right? What's really the ongoing things that are being, people are trying to figure out is the challenges is how can you be selective in that when you have a giant molecule? What if you only wanted to functionalize a certain part of it, right? That's what people are going after, right? And also in terms of asymmetric stuff, right? How we could form certain enantiomers over another, and obviously catalytic type reactions where you could use some sort of catalyst to do a reaction cycle, right? So it's relatively cheap than having to do a one-to-one type reaction, right? So a lot of this chemistry is like, this is why it's taught in textbooks, because it's kind of definitive organic chemistry that laid the principles for everything. Now, the things that are kind of being researched now is how can we make this more selective? So, we could use this in, drug synthesis or, some sort of other bioactive compound synthesis, pharmaceuticals, etc. Okay, so let's just do a couple of these Michael additions. I don't think. Around 21.35 is okay. So yeah, we'll do this. I'll see if there's another one example. And then really what I'm just going to end at is, did you guys do the Robinson annulation in class? Anyone remember? It's this gigantic polycyclization reaction. It's an internal Michael addition, essentially. Anyone remember if you did that? I'm just kind of curious because I do. Was this one? I want to say it was this semester. Yes. So if this was covered in your class, right, back in that section notes, that is a full mechanism for an example for a Robinson annulation, right? If I tried to attempt to write this right now with the current setup I had, it's probably going to take like half an hour or something. So I'm not going to be doing this example, but this is your example, I think from your book actually, or maybe a similar example. And so you could always kind of look at this, right? So what it really is, it's a Michael addition followed by an aldol condensation, right? So if you want to like practice it and then look at the answer, it would be over here. And then what else did we have back then? Yeah. Kind of ended at Clayson's over there. Okay, anyways. So here, let's do example, a couple of these Michael additions. right? Okay, so you have this. Okay, so those are your conditions, and we're gonna just do 3 examples of those, I guess. Uh, yeah, we'll do the next one here too. So okay, this is, there we go. Okay. So yeah, just put A and B through those conditions, right? If you want to look at the table to see what the purpose is, right? Just the main thing is understand it's going to attack at the beta position, right? So take a minute or two to just draw out the products for that. You're going to be using that Gilman for both, right? So that's really, I don't want to give away everything, right? But that's going to be your Michael donor. Okay, so the first one, right? Essentially, you could consider like a Gilman reagents, the CULI, the cuprates here, right? They kind of similar to Grignards, right? There, you could just say they're like delivering. Oh, it's like having a ethyl carbanion, right? That attacks over there, right? It's gonna push up, right? Form this, right? Technically, you will have a enol there, right? And that's what the H plus is for, is to basically kind of tautomerize the enol back into a carbonyl, right? So all it really is, the outcome of this reaction is that you're installing whatever your Michael donor is at that beta position, right? So here, our first product should look like ethyl 1,2, right? And then the next one, right? Same thing with ethyl. Now our beta position's here on this ring, right? So the only difference here, right, is going to be the structure is slightly changed. Okay, yeah. Probably just do one synthesis question because this is just kind of getting ridiculous at this point. One should be, no, hold up, it's a 6-membered ring. The original problem had a 5-membered ring. There you go. That is not a aromatic ring. That is just a regular alkyl ring, despite all the attempts to make it look like a single line, right? So one thing to note is kind of, once again, get you guys thinking. Instead of if I used a Gilman reagent, right? Let's say I used, I used ethyl magnesium bromate, bromine, or ethyl Grignard, right? Where is that going to react? Is it going to react at the same position, or is it going to react somewhere else? So I'm not sure if what you meant by the 1,2 addition, where you meant, but yeah, but nada is correct there, right? It's going to react with the ketone, and this is why this Michael. That's why I said it's all about selectivity in what you use, and this is why the Michael donors are very specific in how they're kind of arranged, right? Is whether they're the Gilman or these dicarbonyls or everything, right? They're selective to that beta position there, right? This position here that I'm circling, right? They will never react with the carbonyl. But a Grignard we know is a very, very strong nucleophile, right? And that will react with the carbonyls in both of these questions, right? Problems, right? So you would, if you know, I don't know if he'd put a trick question like that on it, but it's just something to consider, right? That understand like what makes a Michael donor, right? As opposed to other types of nucleophiles, right? So a Grignard would just react with your carbonyl, and it would just form your alcohol, right? Then you'd get a alcohol product that looks like, would be your Grignard group, this is your other group, and you'd still actually have unsaturation here. So that would be the product if you got a Grignard, right? Just things to think about, right? In terms of what to use or whatever, and trying to remember, like if you have to do this for like a synthesis type question, right? Don't use a Grignard, or don't use powerful nucleophiles, right? That are, not selective. Okay, so let's just end with one synthesis question. Let's see which one I want to do here. Let's do one synthesis question. By the way, once again, as you guys saw from this previous exam, those suggested problems, right, might be the same thing that happens on your third exam, right? So just things to think about in terms of practicing on your own, right? Um, okay, we'll do 21.42b. That's not too bad. It's actually should be, I'm just looking at it. I think it should be 3 to 4 steps. Okay, so it's a 21.42b. All right, let's say so it says to start with cyclopentanone, right? So cyclopentanone, right? Is this, right? And your final product is gonna be I'm just gonna abbreviate this as pH since it's there we go. Okay, so you're starting with cyclopentanone and you're gonna end up with this product, right? So first thing, right, between cyclopentanone and this, what kind of bond did we form? So what we did here was essentially we're forming this, it's kind of the key bond here, right? Um, and one thing to kind of look at here, right? Is what's different here, right? I guess is this OME, which you guys probably haven't seen before, but I mean, it's still nothing hard, right? It's just thinking about what happens in these steps, right? So if we were to do, there's a couple ways we could do this. Technically, we could use aldol, probably use a Clayson too. And what else? Nah, I don't know if you could do it through a Michael addition, possibly, but yeah, you could probably. Well, the thing with the alkylation reactions, the kind of issue here though is you have this OR group here, right? So the alkylations usually work with just pure alkyl halides. So there's no additional O group there. I mean, technically, maybe you could like brominate it and then, install the OME group or whatever, right? But usually you wouldn't have something like BR or X next to directly your OME. right? And then your R group or whatever, right? It's just usually pure alkyl halides, right? There's no additional groups there. So that's why it has to be one of those aldol reactions or Claisen too. But, we could just keep it simple and make it an aldol. So remember what we did last week, right? As if we were trying to break up this aldol reaction, right? We could cleave this bond, right? And then we would have something that would basically look like OMe on one side, right? And then you'd have your H would be the other part of this carbonyl, and then the pH group, right? Yeah, just making sure. So, and then obviously your cyclopentanone, right? But the kind of issue here though is like we've never really seen this before, right? Is this OMe, right? So most likely it wouldn't come from OMe, right? Because this first of all, this would have a plus charge here anyways, right? Because it's alkylated. So realistically, it would probably come from an aldehyde like that looks like this. This is where you would have to play around. Like obviously, this is a much more simpler synthesis problem, but I just liked it because they had this alkylation that occurred, right? So the first step, you could use any base. You should be fine with using NaOH, LDA, NaH, right? I personally just like using NaH for the aldol type reactions. I mean, I think you guys should probably just stick with NaOH if you can. I guess NaOH is fine too. The reason I like NaH is because it's non-nucleophilic, so you don't have to worry about the OH attacking your carbonyl and then making something else, right? So I'm just going to use NaH here. LDA would be fine. NaOH, NaOET, any of those should be fine, right? You just need the strong base to deprotonate it. So then after step one, what happens is you form your enolate, which we will draw in the carbanion form, right? Right. Now if we attacked our aldehyde here, right? Right. So the best part about this reaction is that, the aldehyde, right? Because it's a phenyl group on one side, aldehyde on the other side, you don't have to worry about this getting deprotonated, right? So this is just going to attack, push up, right? And now we get this. And this is why it's important to think about these a little bit in terms of their intermediates or mechanisms, right? Because now we formed our desired bond here, right? pH group, right? That's a minus charge there in case it wasn't clear, right? And now this is why, like, because so typical in the aldol reactions that we did earlier, right? Well, what's the step followed by your actual addition part? What usually like what are the usual reagents we use? Or what do we have present, right? That could make this a beta hydroxy ketone, right? So how do we usually get this O minus to OH? We need what? proton source, right? And that's usually water, or a second step that says acid workup or water workup, right? So this is the kind of key with understanding what they did different here was now instead of that H2O step or the H plus or having this in any sort of aqueous conditions, right? All you could really do here, right? What would be just different, right? Is you could just methylate this directly because now let's say if this was in completely anhydrous condition where there's no additional protons for this to protonate into an alcohol, you would be left with this O minus intermediate. So now what you could do is you could just basically quench it with an alkyl halide, in this case, something like methyl bromide or whatever, right? So yeah, we'll just use methyl bromide, right? And then this is just a simple SN2, it attacks the methyl, kicks off your BR, and you get your final product, right? Which is over here. So it's actually 3 steps, not 4. I guess with Clayson, it might have been 4, but yeah, pretty straightforward. That's why, you know, it's better to understand what each step does than just memorizing a set of reaction conditions. Because yeah, when you see aldol, you see base, water, right? You get your alcohol or your alpha beta unsaturated ketone, whatever it might be, right? But there's a purpose for that water, right? So if instead of using water, you introduce an electrophile there, then you could get this kind of ether. I guess it would technically be an ether here, right? So this is the kind of things to think about in case you get some sort of kind of tricky synthesis or, you know, synthesis you might not see, right? Just like I said, just think about how things act. This is a nucleophile, this is an electrophile, right? That's why I know I've said this so many times and I keep repeating it, but it's the best way to approach all organic chem problems. This is understanding what the role of everything is in a reaction or problem or whatever you're given. And then you could always kind of figure out what happens. Okay, we're going to end here.